What's up, everybody? Welcome back. Woo! Start the day off with funky music. What's up, everybody? Welcome back to the stream. I haven't streamed all week except for the Sunday Fun Day Pipistrello stream because I was doing a little bit of uninteresting work. I figured maybe I should do a study stream or something like that. I know it's kind of uninteresting. I realize that a lot of the stuff I do is kind of uninteresting, especially on a day-to-day basis. But you know how it is. I figured I was starting to procrastinate a little bit on a lot of the stuff I'm doing, so I figured to hold myself a little bit more accountable, I should do a stream. So here we are today, back at it doing the stream. So let's start off with what's been up in the past few days. Nothing too interesting. I've been working on this paper. Okay, so what I'll do is maybe I'll tell you what I've been up to even from like last week. Last week I did a showcase on something that's a little bit more upscale or higher level than what I normally do. So as you know, I'm a PhD candidate and I work with greenhouses and farming technology and plant science kind of things. This last Friday, I'm part of this fellowship called the Blue Fellowship Building 21, and on that we look at more on the philosophical side of like technology rather than model building and model implementations. So last week I was part of this showcase, and I'll show you the website now. So let me show you. So I kind of made this web page if you ever want to check it out, but I talk about on the higher level of implementing ethical AI systems, especially for agricultural autonomy. And in the showcase, I made 3 different papers talking about what makes AI systems ethical and this concept of AI alignment. And I give like my perspective based on a lot of the literature that exists recently. And yeah, so if you ever want to check it out, it's there. And I kind of apply that to the agriculture industry. The project is ongoing, so it's a bit unfinished. So if ever you want to check it out, this is what I did on my website here. And basically, the idea is future building, imagining ethical AI alignment applied to agriculture autonomy. And I kind of talk about what I do for work, kind of my perspectives on the discussion of AI alignment, and what kind of futures you want to expect, just based on the social failures that exist on current AI systems, and how we see the future, and look at things like how we imagine the futures. Like, do we think about industrial utopia, a cyberpunk dystopia? And I'm more on this side of things called like the solar punk future. And the idea is you don't want to just talk about ethical AI just based on the development side of things, but you also want to talk about it in terms of like governance and things like that. And I would like to apply it towards challenges in food scarcity. So looking at higher level things, how do we tackle issues, things like food deserts, instead of just using greenhouses for production for what is it called? mass manufacturing or mass production just for groceries and stuff that are high priced, and how do we actually tackle the issue of food scarcity. So this is the project. You could check it out. Like I said, it's not so much a implementation of models, but more discussing the overall implications of using AI models, especially in my field. So it's an ongoing project. If ever you're interested, you could check it out. Other than that, what have I been up to? I'm doing something in secret that you'll hear about in the future. I might be working for a greenhouse soon, actually. So we'll have some interesting updates on that as well. And yeah, so we'll I'll keep you guys updated on that. We'll see how it goes. I've been playing around with the books. I think I've been using it for quite a bit now. I starting to like it a lot. Just to give you an idea of what I've been up to on this, I've been reading One Piece. I started from the beginning. So let's see, One Piece. So I've been using this app. I forget what it's called. But yeah, so I've been using it to read One Piece. And to be honest, that's what I've mainly been using this books for reading manga. And honestly, it's a pretty good experience. I like just opening it up and just starting to read. It's pretty cool. I also been using it to read research articles, which is pretty dope to use. Honestly, it's pretty good for reading and taking some notes. I will say, because it's not like an iPad and it's not like a Samsung tablet or anything, the interface is not very responsive. It's very slow. So you have to get used to it. And to be honest, I don't know how long I don't think I'll get used to that slow interface. I guess this is the one drawback of using like these ebook tablets, which is fine, but it just gets used to it. You don't feel like you're using an iPad, you know? And I guess I know that's not the point. The interface is not like the most easy to use, and I still get kind of confused about it. But hey, it's kind of a replacement of a real notebook, so I think so far it's not bad alternative to just using a notebook. And I have unlimited notebooks, right? So I don't need to carry a bunch of written books like I used to, like this logbook that I had written. I will say there is something to having something like this that feels more natural than to having, you know, this pad where everything's saved as a file. I'll keep using it and I'll keep updating you. I will say I don't use it every day, but it's not like I was using this book every day either, so, and I tend to forget to use this book. So all in all, it's a good replacement. It's a good replacement. It just, you have to get used to how to organize your works and stuff. Like I said, it's not as seamless as like an iPad, so it's very hard to like integrate this into your, I don't know, your technology consortium, you know. So it's not as seamless as you would think. Yeah. So if you're gonna get the books or any tablet, I wouldn't think of it as an iPad. But it's good. It's good. It's not bad, honestly. Taking notes side of things, I've used it less for taking notes. It's mostly for reading. Let me show you like what it looks like with like reading research articles. And I kind of like this because I have all my research articles here. I can take notes on them. I don't have to have a physical copy where I leave it behind. I don't know what I wrote. I can always pull it up, and I reading like these research articles, and it's very nice. It's very nice to read research articles. Like I said, it's still hard to, but this has nothing to do with the tablet, but just finding that good workflow between taking notes and reading. You know, it's not like I have 3 monitors where I'm reading on this monitor and I'm writing on this monitor. So you know, it's not so responsive that it seems seamless where I can switch between my notes and reading, like as if you were to have an iPad. But if it's good for like highlighting things, taking quick notes on the page itself. Like I would maybe still have a computer or a laptop to take the notes down, but I feel like that might defeat the purpose a little bit. It is really good. It is really good for, let's say, just reading manga or reading your books in itself, which I think is the primary reason for having this, which is not bad. Okay. And jotting down quick notes and stuff. So I've been using it. It's pretty good. I'll give you a hint about what my secret project is. Look, I'll show you this, and that's all I'll show you. That's it. That's my secret project. That's all you're gonna see. So like making quick sketches, you know, it's a pretty good tool. It's a pretty good tool. How is the audio on this? So it, like I said, not bad. Not bad. Okay. Other updates, like I said, I'm talking with a greenhouse right now that might want to work with me, so I'll have more updates on that once I get more information. Drink my water. And like I said, I've been working on writing a paper, academic paper. So this will be today's stream, mostly working on the academic paper. Alright. I've been talking quite a bit. Let me... Yeah. Any other updates? No updates per se. I think... Oh, I should respond to this email. I'll respond to it in a bit. In terms of how I'm feeling these days, it's so hard switching between projects that I get like this analysis paralysis, and sometimes I feel like I procrastinate a lot when I'm in that analysis paralysis mode, and it's very hard for me to just work straight up and not think about 10 different things going on at the same time. And maybe that's just what it means to be a PhD. Because a lot of the work is driven by your own ideas and your own projects that sometimes there's no like clear define what's the next step, and I'm trying my best to do that. I'm trying my best to do that. So we'll see. We'll see how it goes. So with that being said, I guess we can start like doing our study stream. So here I'm working on this paper, and what we'll do is we will, what is it called? Stage timer. I'm gonna reset the stage timer. So let's do some work doing a little bit of paper writing. I'm not gonna continue doing it all day. Like, let's say we do 2 work sessions on it, and then maybe I might end the stream there. So we'll do like 4 hours, 30-minute breaks in between, and we'll see how it goes. Like I said, with this work streams, it's a bit my way of making sure I focus on something. And yeah. And like I said, I've been procrastinating. It's not so good. So we'll get started soon. I know I'm like babbling a little bit. This is another way of me procrastinating a little bit. All right. I have my water. Well, honestly, talking to the stream helps me get my thoughts out there, which is pretty nice. And I feel like I'm actually doing something. So yeah, we'll get started. I'm gonna refill my coffee. I'll set up the study stream. I'm just gonna go get coffee. I'll be right back. I'm just gonna fill it up. All right, so let's get down this way so you can see. You don't even have to follow me anymore. Put this in the back a little bit. Yeah, so study stream. Yeah, so the reason why I'm doing paper writing, even though the project is not quite done, is it kind of helps me frame what message I'm trying to. Whew, this is hard. There we go. Down here. It helps me frame a little bit of on like what I'm trying to message with my project. Think of it like documentation. So this project is not completely done. I'm writing on a paper on the actual platform itself, and I'm kind of writing out the ideas of it, the structure of it, and then once that's done, hopefully I'll try to publish it, and I'll get data from my platform, and then we'll see how we go from there. All right, so come study with me. I'm going to be working on this. You can see me on the bottom right corner of the screen. It's not going to be blasted huge because the whole point of this stream is you can study along with me. All right, so let's get started. I'm going to start the timer, and then we could keep it pushing. You know what I'm saying? Keep it pushing, y'all. All right, let's get that started. All right, guys, study with me. Good luck, everyone. We'll start for 2 hours, then 30-minute break, another 2 hours. Cool? Tests within plant phenomics research often require the observation of spatial temporal patterns across these and a combination of factors that influence their dynamics within adaptive crop systems. Spatial models have leveraged state-of-the-art empirical methods and computational frameworks for predicting the expression of plant traits, encompassing various plant health indicators, measures of biomass, and overall growth dynamics. Machine learning techniques such as regression support vector machines and neural network-based approaches and have been particularly effective in capturing complex nonlinear relationships between. These models are designed to provide insights for optimizing agricultural production methods and help improve crop yields. In prior review of works covering recent state-of-the-art spatial temporal pattern recognition techniques for modeling plant growth phenotypes, we assert that the shift towards data-driven models, particularly deep learning models, have placed significant dependence on the availability of diverse representative datasets for training and validation. While advancements in high-throughput plant phenotyping technology is commonly associated with computer vision and sensor fusion-based methods for obtaining images, point clouds, and auxiliary data, there remains various challenges that create bottlenecks in the accessibility and consolidation of high-temporal resolution data across scopes of research and crop varieties. Due to these challenges in collecting consistent spatial data over time, the focus of phenomics research is often limited to classification tasks such as detection and segmentation, with limited works done on predictive forecasting and temporal analysis. In this work, we aim to address one of these major bottlenecks within the high-throughput plant phenotyping plant growth modeling pipeline. The systematic observation, acquisition, and standardization of temporal multimodal datasets. To achieve this, we propose an open source framework and standardization protocol, which we demonstrate through our controlled heteronic imaging platform. It encompasses the physical systems, the underlying design principles, and data aggregation techniques for capturing high-resolution spatial temporal plant growth datasets. This paper outlines the contributions of this work and is organized as such. We outline an replicable and framework for collecting errors. We present a standardized data acquisition pipeline that facilitates the collection of results. We demonstrate the application of chip to. Okay. forefront of data collection advancements in plant phenomics research. These platforms are typically categorized as on-the-ground field platforms, indoor conveyor platforms, or remote sensing satellite or droning imaging systems. They are often equipped with a variety of sensors, including cameras for visible, near-infrared, and hyperspectral imaging, as well as thermal cameras and light-detecting ranging scanners to capture a diverse range of spatial parameters within the plant system. The simultaneous integration of these parameters are used to develop inference models for predicting functional plant traits, which in turn can provide a comprehensive overview of the plant state within a growth system. Moreover, data fusion techniques are employed typically through DL approaches, which combine multiple modes of data as input within a feed-forward process. These models represent a step forward in plant research, demonstrating improved accuracy of a variety of inference tasks, including 3D point cloud segmentation and yield prediction. An inherent shift towards data-driven methods is evident with recent works utilizing the data frameworks introduced by high domain precision. These methods have typically improved accuracies in trait prediction models and overall efficiencies of information processes when compared to traditional data collection and modeling approaches. Advances in CV, particularly the integration of convolutional neural networks, have enabled the extraction of phenotypic traits. Moreover, 3D imaging techniques, including structure for motion or stereo vision, provide methods for processing spatial information to produce reconstructed 3D representations of plant structures. Sensor and data fusion methods complement these imaging techniques by providing continuous non-destructive monitoring of contextual conditions to improve model accuracy. For example, environmental sensors can be used to continuously monitor contextual growing conditions and be employed within an environment-driven model for forecasting plant development. That's good. Honestly, I think I wrote a good introduction. And the next step is kind of laying out the actual work. Okay, so related works. Other works have similarly explored the development of phenotyping platforms to address the data bottleneck found within data-driven plant research. These works serve as a baseline for the development of CHIP and are used to identify the gaps in data collection. The criteria for comparing the phenotyping platforms outlined within these works are as follows. The scope of the platform is to capture the structural development of plant growth within time series images of plant growth within their original growth systems. The system tracks auxiliary growing conditions for observing environmental dynamics corresponding to image data over time. The imaging systems are able to capture more than one view of each plant, particularly for multi-view 3D reconstruction. The system is open source, easily replicable, and presents data standardization and pre-processing protocols for further facilitation of research within the field and the establishment of large open plant datasets. Okay, so this is So what I'm going to try to do is I'm going to try to finish this introduction. Okay. Okay. Platform. What do I even call this? Typical framework used in automated plant phenotyping platforms is the use of conveyor-based imaging systems. Phenotyping platforms. Okay, sorry guys. So I'm working on this part here. So Phenoscope. So in this, I'm still finishing up this introduction, which is basically introducing the concepts and also comparing with existing systems. So right now, the paper that I'm reading is a system that's kind of used in the field that I'm trying to compare it with. It's kind of like related works paper. A typical framework used in automated plant phenotyping. Passes plants through a uniform. Okay, a typical framework used in automated planning is a conveyor-based imaging system. A typical framework used in automated plant phenotyping platforms is a conveyor-based. In these systems, isolated. What's a synonym for isolated? framework used in automated plant phenotyping platforms is a conveyor-based imaging system. These systems are grown in independent, detachable typical framework used in automated plant phenotyping platforms. Scheiße. Okay. A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each individual plant in these systems, are grown on A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown under independent units and pass through an enclosure One such system is demonstrated by Tizenhal's Phenoscope platform. These platforms are typically used in plant breeding operations. A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and pass through a camera enclosure to ensure uniform imaging conditions to extract plant phenotypes. One such system is demonstrated by its cells phenoscope platform. These platforms are typically phenoscope. A typical framework the system is used to A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and passed through a camera enclosure to ensure uniform imaging conditions. To extract plant phenotypes. One such system is demonstrated by its phenoscope platform. This system is used to track growth. Achoo! Achoo! Damn. Ooh, just got an email. All right. Each plant in these systems are grown in independent detachable units and passed through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system is demonstrated by L phenoscope platform. This system is used to track growth and to compare plant genotypes. under controlled conditions. These systems are typically employed under breeding programs A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and passed through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system is demonstrated by Sanel's Phenoscope platform. This system is used to track growth and compare plant genotypes under controlled conditions. These systems are typically employed under breeding programs for desirable genotype selection. A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and passed through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system is demonstrated by phenotype. This system is used to track growth and compare plant genotypes under controlled conditions. Typically employed under conveyor-based platform. In this section, we introduce an integrated system, architecture, and design framework that meet the criteria outlined in. The proposed framework consists of subsystems, which constitute the gross system. Oh, wait, oops. Other works have similarly explored the development of flat phenotyping platforms. A typical framework used in automated planning. Phenoscope platform. This system is used to track growth and compare plant genotypes under controlled conditions and are typically employed under This system is used to track growth and compare plant genotypes under Honestly, this streaming stuff actually helps me focus on this, which is good. A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and pass through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system is demonstrated by this system is used to track growth and compare plant genotypes under controlled conditions. Such systems are employed. Typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and pass through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system is demonstrated by Tisna et al.'s Phenoscope platform. This system is used to track growth and compare plant genotypes under controlled conditions. Such systems are employed in breeding programs and not necessarily for the tracking of crop performance under in situ text IT. It, okay. Such systems are employed in breeding farms and okay. Let's Moreover, the mechanization of an instance of observations. A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and pass through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system is demonstrated by Tisne et al.'s Phenoscope platform. This system is used to track growth and compare individual plant genotypes under controlled conditions for quantitative mapping. Such systems are employed in breeding programs and not necessarily for the tracking of crop performance under in situ growing. Moreover, the mechanization of individual plant growth at the instance level introduces complex. Such systems are employed in breeding programs for desirable and not necessarily for the tracking of crop performance. Moreover, the mechanization of individual plant growth at the instance level introduces complexities which require constraint. Introduces complexities which require constraint. Okay. Okay. Conveyor-based phenotyping platforms. A typical framework used in automated phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and passed through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system, this system is used to track growth and compare individual plant genotypes under controlled conditions for quantitative trait loci mapping. Such systems are employed in breeding programs for desirable genotype selection and not necessarily for the tracking of crop. Moreover, the mechanization of individual plant growth for instance level observation introduces complexities which require constrained growing conditions, such as Okay, let's see. Does that look good? Conveyor-based phenotyping platforms. A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and pass through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system is demonstrated by Tisner et al.'s Phenoscope platform. This system is used to track growth and compare individual plant genotypes under controlled conditions for quantitative trait loci mapping. Such systems are employed in breeding programs for desirable genotype selection, not necessarily for the trafficking of production. Moreover, the mechanization of individual Okay, let me, I feel like this is a bit redundant. Okay. A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and pass through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system is the system is used to track growth and compare individual plant genotypes under controlled conditions for quantitative trait. Such systems are employed in breeding programs for desirable genotype selections. The mechanization of individual plant growth, for instance, self-observation, introduces complexities which require constrained growth conditions such as standardized plot geometries and root volumes. These constraints, while enabling high throughput and repeatable phenotypic measurements, inherently decouple observed plant responses from heterogeneous and dynamic condition characteristics of in situ agricultural production environments. Another common phenotyping. Okay. Bam, 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 bam. Okay, another common phenotyping platform. We're getting close, guys. We're almost done with the introduction. I think once I'm done with this, okay, another common phenotyping platform. Another common framework. Yes, 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 yes. All right. Okay. Another common framework used in plant phenotyping platforms is the spatial camera systems for morphological data. Platforms such as Komatsuna, Komatsuna, Kyushu. Fixed camera systems. About gantry platforms. Okay, a platform that more closely achieves the specified criteria set for the development of the chip. Okay, another common framework is used in platform. Okay, another common framework used in developing plant phenotyping. Platforms is a spatial camera system for biological 3D reconstruction of crop phenotypes. Platforms such as Phenobox embody such systems. Another common framework used in developing plant phenotyping platforms is spatial camera systems for model phenotypes. Platforms such as embody such systems with Body such systems, the configuration. Platforms such as Phenobox. Another common framework used in developing plant phenotype is a spatial camera system for morphological 3D reconstruction crop phenotypes. Platforms such as Phenobox and Wu and Elza demonstrate such a framework, which consists of some variation of a rotating platform captured within the field of view of a camera system. Multi-view imaging to extract 3D model. 3D point cloud maps. I just need to pee really quickly. I'm gonna pause the timer. I'm just gonna pee really quick. I'll be right back. Just need to pee. Alright, I'm back. Another common framework used in developing plant phenotyping platforms is a spatial camera system for morphological 3D reconstruction of crop phenotypes. Demonstrates such a framework which consists of some variation captured within the field of view. Such platforms employ multi-view imaging techniques to extract 3D morphological information from Komatsuna, komatsuna, komatsuna. Let's go. Fresh crops, typically to drink some water. Make sure you guys drink water. All right? Don't forget to drink water. It's important. Employ multi-view imaging techniques to extract 3D morphological information of crops, typically through 3D point cloud maps. Okay. Such. I do want to change something. Okay. These Fallout insights By the way, I'm using Overleaf, so that's why I'm not like... This is a PDF that's generated by the Overleaf, which uses latex. So that's kind of why I always recompile and you see the updated text that happens here. I have the text on the other screen, which you guys can see later. I can show it to you later. Kind of looks like... it doesn't matter. Okay, so these morphological insights are performed at the individual plant level and are limited in the ability to capture in situ temporal growth information, opting for manual These morphological are programmed at the and are limited. For temporal growth information, opting for discrete. And for insights are performed at individual plant levels and are limited in the ability to capture temporal growth information. Temporal growth information. Often discrete. Discrete points within the growth cycle. Okay, 8 minutes and then we'll take a break. Used in developing plant phenotyping platforms is a spatial camera system for morphological 3D reconstruction of crop phenotypes. Platforms such as PhenoBox, Wood, and VS Pheno demonstrates such a framework, which consists of some variation of a rotating plant platform captured within the field of view of a camera system. Such platforms employ multi-view imaging techniques to extract 3D morphological information of the crop, typically expressed through 3D point cloud data maps. These morphological insights are performed at the individual plant level and are limited in the ability to capture in situ temporal growth information and is often performed at manual discrete. Manually at discrete points within. Okay, growth cycle. Due to the logistical constraints, these systems I think I'm good with that. Last one is the Komatsuna here, which is fixed camera system. And I kind of just want to write that and finish this introduction section. Fixed frameworks. Uchiyama et al. Fixed camera frameworks such as okay, 1 minute, 1 minute. I am gonna extend just by a little bit because I want to finish this introduction completely. And then after the break, I can read the introduction and move forward. But we did quite a lot in 2 hours, so I think I'm pretty happy with that, if I'm gonna be honest. I'm gonna just increase the time by like another let's say 10 minutes. All right, just because we're on a roll here. Okay, fixed camera frameworks such as Uchiyama's Komatsuna platform are employed for observation of plant performance within a consolidated growth system. These systems allow for plant trait extraction in situ, text IT, in situ plant trait extraction. Okay. Fixed camera frameworks such as Uchiyama's are employed for These systems allow for in situ plant trait extractions in their original growing conditions. Camera systems. Fixed camera frameworks such as Uchiyama et al.'s Komatsuna platform are employed for observing plant. However, these systems are limited Fixed camera frameworks such as Uchiyama et al.'s Komatsuna platform are employed for the observation of plant performance within a consolidated growth system. These systems allow for in situ planting and camera systems that passively perform observations. However, these systems are limited in the number of observable views. Typically opting for top-down or oblique views. To capture more views, more cameras must be employed. predetermined fixed. These systems are limited by the number of predetermined fixed views of the crops, and system typically opting for up-down. To capture more views, more cameras. Conclusions. Fixed camera frameworks such as the GMADL are employed for the observation of performance within. These systems allow for plant trait extractions by employing camera systems that passively perform observations of multiple crops within. These systems are limited by the number of predetermined fixed views of the crops within the system, typically opting for top-down or oblique views. To capture more views, more cameras must be installed, leading to occlusions. Leading to occlusions and loss of morphological. To capture more views, more cameras must be installed. Fixed camera frameworks. Frameworks are employed for systems that limit about the number of predetermined fixed views. Leading to occlusions and loss of morphological information. Okay, time is up, but I'm just going to finish this paragraph. Fixed camera framers such as are employed for the observation of plant performance. These systems allow for in situ trait extraction. These systems allow for in situ plant trait extractions and correspondence with by employing camera systems that passively perform observations of multiple crops within its original growth systems. These systems are limited by the number, leading to occlusions and loss of morphological information. To capture more views, introducing logistical constraints. As such, these systems are employed for Okay. Okay, I'm done. I'm done. I think I'm done with the introduction. We'll take like a 30-minute break. Let me just reread this quick section here. Fixed camera frameworks such as Uchiyama et al.'s Komatsuna platform are employed for the observation of plant performance within consolidated growth systems. These platforms enable in situ plant trait extraction and correspondence with auxiliary environmental conditions by passively observing multiple crops within their original growth environment. However, such systems are constrained by a limited number of predetermined viewpoints, typically relying on top-down or oblique camera perspectives. This results in increased occlusions and the loss of morphological information at the individual plant level. Expanding viewpoint coverage requires the installation of additional cameras, which introduces logistical and infrastructural constraints. Consequently, fixed camera systems are primarily suited for canopy level monitoring, with limited applicability for detailed Okay, I think I'm happy with that, to be honest. Okay, 30-minute break, y'all. We're gonna take a break. Let's see. Where's the timer? Okay, be right back, y'all. 30-minute break. What's up, y'all? We're still gonna take a break because I got some food, so y'all gonna watch me eat and we'll talk. Alright, so we'll continue this, but we're gonna continue the break a little bit. Maybe add like 5 more minutes. Alright, so today I have like a curry pilaf that my mom made a while back that was frozen. So I'm just eating it. Pretty good. So I mainly just did the introduction for a paper. I finished it today. Which is kind of comparing similar systems to what I'm making now, which is the growth systems. And it's not like a review or anything, just like quick comparison of like what kind of systems are available and how my system can improve upon those older systems. After this, I probably won't do the full 2 hours. I'll probably do some work. We'll see. But I don't want to spend the whole day working on a paper. So I might end it early and focus on something else. We'll see. Oh. Little mukbang stream, you know how it goes. I hadn't eaten lunch, so I figured I would extend the break a little bit. I guess the difficulty in all of this is that I need to finish this system. And it requires me to be somewhere to be able to develop it. But at the same time, I also need to work on these papers. And I like this ideal setup I have at home with multiple monitors to write a paper. So it's a bit, I guess it's good in its own way because at least I don't get distracted. But there's just so much that I gotta do. You know what I'm saying? I also need to respond to emails and coordinate with people. It's a bit tough. Who knows? Alright, I finished eating. I think the 5 minutes was good. Okay. Publication writing is hard, man. You have to write so much. All right. We can get back to working. Let me start the other session. Oh, okay. Work session. Break is over. Let's put that back. Still trying to figure out how to make my streams interesting. I think it's like a little bit temporary right now. I think this season is a bit boring, you know? But hey, I'm here for consistency. Am I right? What the hell is this? Hope? Digital phenotyping platform. Monitoring. What the hell? What the helly hell? All right, I'm gonna start by reading the intro over, seeing if it's all coherent, and then we'll move on to controlled environment and growth monitoring systems. Or, yeah. I wonder. I don't want to speculate on anything. None of these papers are cited, man. I think all these like crop segmentation models are becoming a little bit saturated now. Not gonna lie. That's why I kind of want to move towards more fundamental stuff. Just because like we're doing things that are just applied science that okay. So work for about 2 more hours. Hopefully it'll be 5 o'clock, I guess, by then. And I'll end the stream there, and then we'll pick it up after. Modeling tasks within plant phenomics research often require the observation of spatiotemporal growth patterns across diverse plant varieties in a combination with factors that influence their dynamics within adaptive crop systems. From these observations, recent plant observation models to buy more of this. From these from these okay. Modeling tests within plant phenomics research often require Plant observation models have, from these observations, recent plant observation models have leveraged state-of-the-art to predict the expression of plant traits quantitatively, encompassing various plant health indicators, measures of biomass accumulation, and overall growth dynamics. These data-driven methods include machine learning techniques such as regression, support vector machines, and neural network-based approaches, and have been particularly effective in capturing complex nonlinear relationships between environmental factors, genomic factors, and plant growth. These models are designed to provide insights for optimizing agricultural production practices and help improve crop yields. In a prior review of works covering recent state-of-the-art spatiotemporal pattern recognition techniques for modeling plant growth phenotypes, we assert that the shift towards data-driven models, particularly deep learning models, have placed significant dependence on the availability of diverse and representative datasets for training and validation. While advancements in high-throughput plant phenotyping technology is commonly associated with computer vision and sensor fusion-based methods for obtaining images, point cloud, and other auxiliary data, there remains various challenges that create bottlenecks in the accessibility and consolidation of high spatial-temporal resolution data across scopes of research and crop varieties. Due to these challenges in collecting consistent spatial data over time, the focus of phenomics research is often limited to classification tasks such as detection and segmentation, with limited works done on predictive forecasting and temporal analysis. In this work, we aim to address one of these major bottlenecks within high-throughput plant phenotyping growth modeling within the plant growth modeling pipeline, the systematic observation, acquisition, and standardization of temporal multimodal datasets. To achieve this, we proposed an open-source framework and standardization protocol, which we demonstrate through our controlled hydroponic imaging platform that encompasses This framework encompasses the physical systems, the underlying design principles, and data aggregation techniques for capturing high-resolution spatiotemporal growth datasets. This paper outlines the contributions of this work and is organized as such. We provide an underlying conceptual framework and design principles behind it. We outline an easily replicable open system framework. We present standardized data acquisition pipeline, and we demonstrate it. Background: advances in data collection platforms. High-throughput plant phenotype platforms are at the forefront of data collection advancements in plant phenomics research. These platforms are typically categorized as underground field platforms, inter-conveyor platforms, or remote sensing satellite or drone imaging systems. They are often equipped with a variety of sensors, including cameras for visible, near-infrared, and hyperspectral imaging, as well as thermal cameras like scanners to capture a diverse range of spatial parameters within a plant system. The simultaneous integration of these phenotypes, which in turn can provide a comprehensive overview of the plant's state within a growth system. Moreover, the simultaneous integration, which in turn can provide a comprehensive overview of the plant state within a growth system. Moreover, data fusion techniques are employed typically through DL approaches, which combine multiple modes of data as input within a feed-forward process. These models represent a step forward in plant research, demonstrating improved accuracy of a variety of inferencing tasks, including 3D point cloud segmentation and yield prediction. An inherent shift towards data-driven methods is evident with recent works utilizing the data frameworks introduced by Hydro. These methods typically improved accuracies in trait prediction models and the overall efficiency of information processing when compared to traditional data collection and modeling approaches. Advances in CV, particularly the integration of convolutional neural networks have enabled the extraction of phenotypic traits such as leaf area, plant height, and disease symptoms from high resolution images. Moreover, 3D imaging techniques, including structure from frame from motion and stereo vision, provide methods for processing spatial information to produce reconstructed 3D representation of plant structures. Sensor and data fusion methods complement these images techniques by improving continuous non-destructive monitoring of conditional conditions to improve model accuracy. For example, environmental sensors can be used to continuously monitor contextual growing conditions and be employed within an environment-driven model for forecasting plant development. Other works have similarly explored the development of phenotyping platforms to address this bottleneck found within data-driven plant research. These works serve as a baseline for the development of the chip and are used to identify the gaps in data collection. The criteria for comparing the phenotyping platforms are outlined within these works. The scope of the platform is to capture the structural development of plant growth through time series images of plants grown within the systems track auxiliary growing conditions for observing environmental dynamics corresponding to image data over time. The imaging system is able to capture more than one view of each plant, particularly for multi-view 3D reconstruction. And morphological assessments. The system is open source, easily replicable, and presents data standardization and pre-processing protocols for further facilitation of research within the field and the establishment of large open plant datasets. Conveyor-based phenotyping platforms, Phenoscope. A typical framework used in automated plant phenotyping platforms is a conveyor-based imaging system. Each plant in these systems are grown in independent detachable units and pass through a camera enclosure under uniform imaging conditions to extract plant phenotypes. One such system is demonstrated by Tisne et al.'s Phenoscope platform. This system is used to track growth and compare individual plant genotypes under controlled conditions for quantitative trait loci mapping. While such systems are employed in breeding programs for desirable genotype selection, the which requires constrained growing conditions such as standardized pot geometries and root volumes. These constraints, while enabling high throughput and repeatable phenotyping measurements, inherently decouple observed plant responses from the heterogeneous and dynamic condition characteristic of in situ agriculture production environments. Morphological 3D reconstruction platforms. Another common framework used in developing plant phenotyping platforms is a spatial camera system for morphological 3D reconstruction of crop phenotypes. Platforms such as et al. Phenobox, Ewu et al.'s MPS Pheno demonstrates such a framework, which consists of some variation of a rotating platform captured within the field of view of camera system. Such platforms employ multi-view imaging techniques to extract 3D morphological information of the crop expressed through 3D point cloud data maps. These morphological insights are performed at the individual plant level and are limited in the availability to capture in situ temporal growth information, and is often performed manually at discrete points within the growth cycle. Due to the logistical sampling constraints of these systems, contextual auxiliary information such as environment, are not collected or decoupled fixed camera system. Fixed camera frameworks such as Uchiyama et al. Komatsuna's platform are employed for the observation of plant performance within consolidated growth systems. These platforms enable in situ plant trait extraction in correspondence with auxiliary environmental conditions by passively observing multiple crops within their original growth environments. However, such systems are constrained by limited number of predetermined viewpoints, typically relying on top-down or oblique camera perspectives. This results in increased occlusions and the loss of morphological information at the individual plant level. Expanding viewpoint coverage requires the installation of additional cameras, which introduces logistical and infrastructural constraints. Consequently, fixed camera systems are primarily suited for canopy level monitoring with limited applicability for individual plant phenotyping. Mobile gantry platforms. A platform that more closely achieves the specified criteria set for the development of the chip is an automated system developed by the system is comprised of a multifunctional robot gantry system for managing the irrigation, weighing, and imaging of plants grown within the system. The growth system is designed to capture the top and side views of 500 potted plants and automatically records environmental conditions. While some data sets constructed from studies using are publicly available, the complex and closed technical systems which comprise Phenopsys make it difficult and costly to replicate. An affordable and open source alternative to Phenopsys is PhenoCave, an automated imaging system for tracking plant growth developed by researchers. PhenoCave also relies on a robotic gantry system, however only captures top view images of potted plants while monitoring basic environmental parameters. The system's primary function is the top view, tracking of plants through images, making it easy to replicate for plant researchers. However, the trade-off for the system is the lower level of extrapolable information from the data, which prevents certain analysis, such as multi-view analysis and environmental control analysis. Okay.
Hey guys.
Need to go up there. Need to go up there, please. We introduce an integrated systems architecture and design framework. Hmm. Introduce and integrated systems. We propose the integration of the following principles: system modularity through system modularity through In this section, we introduce an integrated systems architecture and framework that meet the criteria outlined to encompass such a system. We propose the integration of the following design principles: systems modularity to edge. To address these requirements, we proposed the integration of several guiding design principles. Okay. In this section, we introduce an integrated systems architecture and design framework to address these requirements. We propose the integration of several guiding design principles. To distributed edge hardware, consolidated information processing to support scalability across life, and human-centered software tools designed to ensure replicability. The proposed framework consists of 3 interacting subsystems: a controlled environment growth system for crop cultivation, a mobile gantry-based platform and a system control interface with an integrated information.
In South Korea, they make
Okay. I think I'm at a point in the paper where I need to do continued development a bit, but I think I made like a pretty good framework um, that that I can follow, and it'll be easy to finish this paper once everything is developed. So now I think the main thing is to just focus on the development of this system itself. So we'll start with that. I think that's good. Like, I can continue adding stuff, but I think that's pretty much good. I think that's good. We'll keep it at that, and we'll continue a bit after. But I'm happy with the introduction. I think I'm done with the introduction. Introduction, background, and some related works, you know? And those are good figures. Fixed camera system, multi-camera. Okay, system architecture and design framework. In this section, we introduce an integrated systems architecture and design framework that meet the criteria outlined in section 1.2. To address these requirements, we propose the integration of several guiding design principles: subsystem modularity and expansibility through distributed edge hardware, consolidated information processing to support scalability across large data sets, and human-centered software. Okay, so I think that's good. Note to self: include what data is extracted from each subsystem. Include spatial maps, etc. Okay. I think I'm gonna end it there. I know we still have 1 hour on the clock, but I think I finished what I wanted to do for this paper so far. Now we need to continue development work, so I think I'm gonna end it there. I'm gonna stop the timer, restart it. Okay. Alright, so back to me. I'm gonna end off here. Cool. So I think it was productive. We finished the introduction of the paper. We started a little bit of the framework. I got to a point where most of the stuff now I need to kind of finish development, but it kind of gives me an idea of what kind of stuff I need to produce. Software tools that consolidate stuff for users. Okay, I think that's good. Thank you for joining me on today's study stream, work stream, whatever you want to call it. I'm gonna start working on some development stuff, but I don't know yet what exactly, and I don't want you to just watch me fumble around trying to figure out what to do. So I think I'm gonna end the stream there. So thank you for watching. Let's keep it up, because I find that let's keep this streams up, because I find that I can focus within those times without getting too distracted. So cool. I'm gonna end it there. I want to put a song that... Okay, let me finish it. Alright guys, thanks for watching. Maybe I'll be back tomorrow. Who knows? Tomorrow's Friday. Hopefully, I want to find something fun to do, but I think I need to establish consistency first. So let's start with this. It's not as fun as